Hey, Alexander.
Hello, good morning.
Good morning. Good afternoon. We have Xueying with us today. Or maybe I can, let's see if I can use the fancy camera. And how now do I get Alexander off the big screen? Well, Alexander, you can see yourself. Hey, Chris. I think Xueying, if you raise your arms, it's gonna catch on to you. Let's see. There you go.
Oh, now I see. I am in the big screen. You're off.
You are definitely on the big screen. What is that on my window? Oh, it's my other screen. All right.
Okay.
Yeah. Very good, people. Welcome to this week's CSLib meeting. Wonderful. Since we don't have many of us, probably because many are on vacation, we can take all decisions to go fast. Just kidding. We can do things that make sense. So, what I would like, I have just a few things to discuss today. Maybe we can talk a little bit about what we're going to do, but let me first share my up here. So I would like to give you some news. Well, I don't know if you are all following up with what's happening with the pull requests. We are merging a lot recently. So basically what's happening is that we first about what we merged. So we've been merging this multi-tape Turing machine PR. I think the relevant people are at Flock, so they are probably not joining. But I think now that I expect the Turing machine part of CSLib to go much faster now. One thing I had to do recently, because and I think I said it also at the last meeting, is that we were merging things a bit slower than expected, and that's because based on how we originally configured the repo, if a PR touched even a single file for which there was a code owner, then that code owner had to put in an approving review. And it just turns out that, perhaps not unexpectedly, since we have a lot of integrated parts in CSLib, a lot of PRs touch on multiple areas, even though sometimes they touch trivially on some areas. I had to stand there and wait and ping people all the time. So now, if I don't think it's necessary, I change the rules such that I can just push the merge button and call it a day. And this is helping. This doesn't mean that I review that I merge stuff that is not reviewed. It just means that if I see that we don't need yet another review because a fix in a file is trivial, then I just go ahead, right? Otherwise, we block people for a really long time. What's been happening a lot recently has to do also with these FLP part of the repo, where basically I've been merging a lot of PRs by Shin-Sun, where he's working on consensus. So he has already proven that he has formulated consensus over arbitrary distributed algorithms. He has proven that, well, actually, there's a wonderful README that we could have a look at. But I've just finished the review in this last PR, and we have reached the point where we have a definition of distributed algorithm for consensus. a definition of consensus, a definition of fair scheduling, a definition of pseudo-consensus, which is consensus, which is fault tolerant, actually, pseudo-consensus. So it's a pseudo-consensus or consensus after a given number of faults. You give a bound to how many faults you can have.
Mm-hmm.
And I've just finished reviewing the PR for this pseudo-consensus with one tolerance to one fault. And I expect after this, because he told me he's basically finished with this, then we have the last file about, still two files. One about impossibility of pseudo-consensus. Sorry, I need to be very careful with my formulation here, so let me read it carefully. So here we want to prove that there's no consensus algorithm that can tolerate even a single fault. And then that instead we can reach consensus if there are no faults at all, I guess. So that's very nice. This would be a full formalization of a pretty famous paper about impossibility of distributed consensus in CSLib. And it's all based on LTS. So we can maybe reuse it. If I remember correctly, the algorithm is defined very generically. It's defined on the transition system of the processes. So we could even plug it in to some languages where we can express these behaviors. So that's very nice. Another thing that's been happening is a lot of progress in the logic part. So with Thomas, I've been working on refactoring completely the way that we use to deal with inference systems, congruence, and logical equivalence. It's not really, all new. It's just a big refactoring to make it more useful. But in this new framework, which is now all here in 753, and this is just a step. Then we're gonna do more, right? But this is already quite big as a PR. So I have changed I have put some pretty printing. That's okay. But I have changed the definition of congruence. So now we have two congruence classes. One just gives you access to the notation, and the other gives you basically the definition of what a lawful congruence is. So it's a relation clause under all syntactic contexts for a given type. Then we have default congruence that registers the canonical congruence for a type. That gives you access to a notation. Let me see if I can show you an example here. Examples. Right. So if you just have a congruence like this relation myrel, then you're going to use the notation by putting the relation as a parameter. And if instead you're the default congruence, you don't need to point the parameter out. It is the default congruence for that type. I have refactored all of Henderson inner logic, classical inner logic, and model logic to adopt this thing because they tested it for a lot of corner cases, right? Because in Henderson inner logic, model logic, and linear logic, logical equivalence is defined differently and in interestingly different ways, right? So that's why I wanted to test it with all three of them. And it works. I think the key of it is that now we have homogeneously for all three logics this concept of logical equivalence, which is now just defined as it's a congruence for a specific system of inference. Okay, and you need to prove to me that if I get a judgment and I replace a proposition with another equivalent one, then it's still valid. That's all it says. That's all we require for logical equivalence. And this means that I could start finally playing with our framework for using all this stuff, which you will find in The first tests are in HML. So here, for example, I'm proving that if you have diamond mu phi1 or phi1 and phi2, then you also have that is valid to say not box mu, not phi1 and phi2. Now, why is this an interesting example for our framework? Well, first of all, the equivalence of these two things, so diamond mu phi1 and not box mu not phi1, that's called as duality in modal logic, right? So I have proved it for HML. If a lemma called dual, it gives you that. But here I'm trying to do something different, right? I have a context. I have this end phi2 that's in the way, right? And the idea is that, well, I should be able to just say that since I have proven it for this little piece and logical equivalence is a congruence, then this theorem should hold basically trivially, right? Just by applying the rule of logical equivalence we have in the type class. And I proved it in two ways. I've proven it in two ways. One is by explicitly pointing out what the context is. So the context is this, right? And phi2, that's the part that remains the same. So I just pointed out, invoke the fact that logical equivalence is a congruence, and then I apply the rule for lifting logical equivalence to validity. And it works. It's quite elegant, but it's very manual. Or you do it with grind, right? Now, the proof with grind is great. It's very succinct, but it relies on the fact that there is this lemma, which basically allows lean to escape by implication from within the language of propositions of HML to leans by implication connected, which is, so it's kind of cheating. It's very automated, but it's cheating a bit because here I'm using only logical equivalence very abstractly. And instead, this guy is escaping to lean and using some properties there. So but it's cheating only a little bit. So I'm hoping to get rid of this. Actually, I'm hoping even for more. I'm hoping to write, to plug into Lean's rewriting tactic framework and MathLib's congruence framework to do this kind of rewritings under judgments. But it is non-trivial. It's non-trivial because in Lean and in MathLib, you're usually just rewriting terms into terms. But here, the soundness of my rewriting is under another relation, the one of the inference system, the one for validity. So it's not an equality. It's just saying that if you had this, that it is valid, then this is also valid. And I couldn't find a way to do this with current frameworks, right? So maybe we have to talk to them or do something new. I don't know. So that's going very well, I would say. But there's all this work in automation that needs to be done. Though I expect that if we could generate verification conditions out of this stuff, right? That would also be a nice avenue to explore for this kind of things to prove that to automatically generate a derivation or a proof. I have also started two other things. One is sorry about the scrolling. So we Shuing here. I'm not sure if you can see Shuing right now. Shuing, raise your hand. There's Shuing. So anyway, with Shuing here, we have finished a formalization of a verified compiler for choreographies for distributed protocols, right? And we started upstreaming bits of it. Now the project is huge, so we definitely can't make a single PR out of it. It's probably going to be 20 to 50 PRs or even more. but there are already bits that are easy to integrate with CSLib, so we just started. The first bit we are doing here is called the stateful processes. It's a simple process calculus where you can write things that look like this. Let me see. I made an elaborator, or I made some macros, I don't remember. Anyway, you have actual syntax, and you can write things like variable x equals expression e. It's a bit like a simple imperative language, but it also has a send and receive, essentially, right? So you can write simple protocols with it, and then you get a semantics. And it's heavily parameterized. So now here it's all stringified. But the language is parameterized over the type of process identifiers. It could be a URL, it could be a bit, it could be whatever, a bit string, whatever. The type of expressions, well, the ground expressions, because we want to be able to escape to Lean and integrate with the crypto primitives that other people are making. The type of recursive variables, the type of values that expressions are evaluated into, and a couple of other things that now I don't remember. Anyway, with this language, which is currently, I just put a fragment just to check the design. We can prove, we have an operational semantics, so we can prove that a program involves in a certain way. And we have concurrency, we have distribution, so they can communicate. It's based on message passing. And that's already useful. So for example, we could, I don't know, model the Diffie-Hellman protocol, where Alice and Bob exchange, well, do computations to agree on an encryption key. And proving that correct would already be very, very nice. Then what we're going to do is the next step is to introduce a choreographic language, which looks like the Alice and Bob protocol notation that people use to write security protocols. And that we are able to compile automatically to this kind of stuff, right? We wanted to have both levels because choreographies are nice to write the protocols and the processes are nice to reason about implementations. We are not going to reason so much about implementations because we're going to have bisimilarity. We're going to be able to reason directly with the choreography. But processes is what is easy to compile to executable implementations. So we're going to write, hopefully, compilers from these processes to Lean or to Rust or whatever we want. So that's the plan, at least, basically. I've also been working a bit on AI because for some things it's gotten quite decent at helping out, especially in writing tests. So you will find soon a PR where I wrote an agents file for everybody to use. And I'm testing it by writing Milner's vending machine. If you're not familiar with it, it's just a very simple concurrent process that receives a coin and then you can order coffee or tea, right? And it's sort of the textbook example that shows you why bisimulation is interesting because you can design it in two ways. This vending machine, either it gets the coin and then you choose between coffee or tea, or you can have a machine that makes a choice immediately at the top, where you give me a coin and then you get coffee, or you give me a coin and then you get tea. And these two things don't behave equivalently, because the first machine, you put a coin and then you can choose between getting a coffee or a tea. The second machine, you put a coin and then it's the machine that decides for you whether you get tea or coffee. It's already decided at the beginning. So these are trace equivalents, They have the same traces, but they're not bisimilar. And it's important that they're not bisimilar because they don't behave the same in a distributed setting. So, so that I'm trying to prove with AI. The AI has been good for some things and was really bad at proving the theorem that they're not bisimilar, but at least it got me halfway there. So we'll see. What I am noticing is that the proofs output by the AI are very stupid. They're incredibly stupid. So they are like 50 lines of code for something I would have done in 3, right? So I think the trick here is that we need to invest more time in offering more examples in how we do things, because the AI couldn't find any relevant examples in MathLib or other projects, right? And I'm not surprised that there are not many lean projects where you can get how to reason about transition systems, for example. Hey, Reyes, go ahead.
Hey, have you tried asking the AI to do the golfing of the proof for you? Sometimes it finds all these interesting golfs when you ask it to do a second pass.
Yeah, I haven't been very successful with that yet, though I've been successful with correcting the AI, like the AI at some point in a couple of instances, it made the proof in a slightly different way than what I would have done, right? And then from there it took a very wrong road. So then it's interesting to accept and then erase the thing and start from there and tell the AI, now do exactly this, right? So with that, I've had better luck.
Okay. So what I do is sometimes I get these long proofs and they are full of change and some halves and such, and then I see that this is a code smell because it's the simple normal form that the lemma statement used is wrong or something. And then I tell it, well, use that simple normal form and then use simp here. Then just grind maximally golf it. And if you give this to GPT 5.5 and 6, it'll golf the proof very well.
Yeah. But this is stuff we should. That's why I wanted to put a shared agent file in the repo, because I've been filling the repo recently with these readmes that should also guide the AI for contributors, but it's also aimed at AI to gain an understanding that we are really interested in reusing APIs across the board, because that's where the AI also had a lot of trouble. It started ignoring that there are other APIs in other parts of CSLib that might be useful, right? Because the AI tries to be focused in its work by default. So I can't ask the AI to read the entire source code of the repo all the time if we get overloaded. But at the very least, I can ask the AI to read all the readmes. Those I'm on purpose keeping small, right? Such that the AI gets useful pointers. And this has helped, actually, in relevant ways. So one big difference I noticed immediately is that the AI, instead of going blind and recreating theorems about the transition systems, by looking at the README in the languages that points out explicitly we are using the foundations found in that directory to do semantics, the AI went and immediately decided to read everything about LTS before going forward, which is what we want, I think. Something the AI has been very useful for has been refactoring. So refactoring Henderson-Miller logic, I did half. The other half was AI helping me out because I needed to refactor it exactly like model logic, right? So in that it was useful. It was a bit of a pain to review because basically you change so much in a file that then you have to read every single line to be sure. And then at some point it started going wrong, but I didn't want to have to reread the entire file. So from that point, I went manual again, right? Because at least I already know what's going on. But I think that at least for something I'm very hopeful for is a bit like they're doing it in LeanZip. So where you have a theorem and you don't care about the implementation of a def, you just, because it's pure maybe. So I'm hopeful about using pure functions to make sure that nothing weird is happening because stuff cannot have side effects. And then using AI to optimize one of these pure functions. And for that in LeanZip, they've had good luck. So we'll see. As long as it respects the specification, of course. And that's where we need to be very, very clever. But otherwise, it's going pretty well. Not a lot of help with API design, I must say. Probably we are still too green with the, well, they are too new. They are very, very much too new. So that's what's been happening, I think, over the course of the past couple of weeks. Just to give a quick recap. There's some stuff where I would really love some help with reviewing. I've asked for some help already in the channels. But there's, for example, something about refactoring, like this one, 731, redefine p-functor free m in terms of p-functor.w. Here it would be very nice if somebody who's been hacking at FreeM, if they could comment on this stuff, right? And I've asked a few people in the chat already, but if anybody would like to have a look, please be my guest, because I think especially in these cases, these are so generic that we risk breaking something that I'm not aware of, right?
P-functor.freem currently exists separately from the other freem. I mean, p-functor.freem is more general, but you need a lot of API before freem can be replaced by p-functor.freem.
Yeah. Exactly. Is our current freem now redefined in terms of p-functor freem?
No. Please don't do that until the p-functor.freem API is stable. It's okay to have two separate.
Absolutely, but I mean, wouldn't it be possible in the future to make it an abbreviation or something like that?
It's a little bit complicated, but yes, it's possible. This was already mentioned by Mikhail Samler in the thread.
Yeah, we're nowhere near even thinking about this. So that's just keeping it in mind as a direction if it ever. But before we do anything like this, we need more code in the repo that uses this stuff. Because
I mean, there's a lot of code downstream that uses this stuff.
Yeah, exactly.
Two full repositories of one my repository and the other is the cryptography repository.
Yeah. So that's also why we need to upstream more and more of the stuff, or integrate it more with the downstream checking. We'll see. But Alex and Shreyas, you are on top of now organizing that call we talked about, right? Okay.
And now we have monadic models as well. So now we can do stateful algorithms like proper query. Like if you have wanted to query a data structure without accessing it explicitly, then this is possible. And this is also great for Turing machines now.
Yeah. Very good.
And all the copyright issues are gone because there's now a PR with everybody's Git somewhere in the history.
Yes, I mean, I'm looking forward to that call. Unfortunately, I've reached out to some people, and I think they're on vacation.
Yeah.
See, but we really need to speed this up because there's a lot of stuff that can be done that we should be doing, and also once so many APIs are fixed, the AI becomes more useful as well because it really needs these boundaries.
There's some 10,000 lines of code downstream on my based on my PR.
Yeah, fantastic. So anyway, please keep me posted. Are there other parts or other things that people would like to talk about that are stuck or anything like that?
I mean, we have 100 PRs now which are open, right?
Yeah, exactly. That's why I'm asking.
So a lot of the open PRs I think are in some sense stale because like they were open many months ago, and like at least 3 or 4 of them are just saying here's insertion sort in time M, which have not been touched.
Why are these untouched? There are at least 3, or I remember at least 3 insertion sort proposals, and I was a bit.
At least one or two of them don't pass the CI, and one of them is. I mean, I think this goes back all the way to February. I'm not even sure if it will compile in the current tool chains. Lots of API changes have happened since then. Like the last time it was run through CI and got the green check, we are 3 tool chains behind the current tool chain.
Okay. But
I mean, I would at least I would rerun the CI and ask merge or I mean, I don't think even Soracha is actively working on time M right now, so it doesn't know. I don't know if it makes sense to drag that up. So there are lots of stale PRs like that, like which were made several months ago, and then I don't think they compile and the authors have abandoned them. Once you remove these PRs, or at least then filtered them out, then you have fewer PRs to look at.
Yeah, I guess we should probably. So the thing is that say now we go back, we look at these PRs and they don't go through CI. Should we review them, or should we just ping the author and say it doesn't run through the CI?
I mean, at this point, I think all those insertion sort PIs are also, I think, fully AI generated. Like somebody threw Claude and older version of Claude.
Yeah.
And
But now we are basically talking about reviewing them, right? I mean,
I think if we abandon let's just be if the author comes back and says, hey, I have this PR, then let's prioritize it, because now there are so many insertion sorts. What is the point? And then which insertion sort PR are you going to pick, and which one are you going to say no to?
that requires looking at the PRs.
I think they're all identical because they're all okay. So before all these PRs came out, I already had insertion sort in my repository, and if you just take that and compile it, you get all these PRs. So I think that's what the AI did, which is a very clever thing.
I see. Okay.
It'll be redundant, but that's what I'm trying to say. I think what I'm trying to say is you can exclude these PRs until the authors show up or something, or we'd merge the algorithms framework and then see if they can port it to this one.
All right.
But it's no. What I'm saying is a lot out of 100 PRs, maybe like 50 PRs are active PRs, and they are the most recent PRs.
Well, then we have some PRs like the soundness and completeness of linear logic phase semantics. Here, I would love some help from somebody familiar with logic. I mean, I could do it, but I'm trying to prioritize PRs where I'm really sure that they are going to be totally stuck if I don't look at them. For example, there was all the discussion about propositional logic, where I had to step in and do actual work because otherwise it would have been stuck forever. Because sometimes I see discussions where what's missing is a generalization, right? And then we have a meeting or somebody steps in and actually makes the generalization to make the PR make sense.
And also, I have an update on the graph algorithm side. I figured out how to work graph algorithms into any model, any of these models. The idea is that you shouldn't actually put graph operations into the timing framework, but you should put data structures like lists, heaps, and queues, and then charge those operations, and then the graph algorithms work perfectly well with simple graph or MATLAB graph. There's no need for an extra API layer.
That discussion is it going forward? I was lost.
No, I think
what was happening last time. Sorachai was working on an example based on graph-like.
Yeah, something like that.
Okay, I'm gonna reach out to Sorachai to understand where we stand there. Okie dokie. We have quite a lot of lambda calculus stuff, but I know Chris Hanson is very busy lately, which shows that we need more reviewers for lambda calculus stuff. By the way, so actually, and then there's some stuff about circuits and asymptotics.
So that's Alex Mayberg's PR. I think he agreed. There was some review comment, and he has agreed to sort of split it into smaller PRs. But it's worth asking him again.
Let me see.
So I want to start adding some first results about time and the relation between time and space. Hopefully tomorrow. And with that, I kind of need to decide how to define asymptotics. And the question is, should I use something from there or not? But I guess we can also change it later on. So
for Turing machine asymptotics, you can just say there exists a constant such that whatever property once holds, right? And then later you can retrofit into a new asymptotics framework.
Yeah, exactly. That's what I'm saying. Yeah, exactly.
At least for all the algorithms I've written, I'm not using any asymptotics right now.
Okay, but I mean, it's kind of sad that this PR is, at least I don't see it in the GitHub thread. Maybe it's been discussed on Zulip that we are going to wait for this thing, but I see a comment from 3 weeks ago asking for whether there's anything else that needs to be done, and something has been done, right? So I mean, what does this PR define?
It's the only criticism against the PR was that it was 3,000 lines long or something.
Oh dear Lord, it is big.
I mean, I would also question whether do we actually need all that, right? It defines tons of growth classes and then close relations between them, but in the end, I don't know. What do you all think?
I think there's already okay. I think it's worth asking Alex because the question is, where does he want to use this? And I think the answer is that eventually he'll combine it with this asymptotic static that is being written by somebody else. I don't know if he's heard of that yet, but the idea is that you can work with on a calculus of asymptotics and prove stuff. But the current most efficient way to write anything related to complexity of our algorithms is to just say, here's a constant and here is a number, and here there exist these two things, and then you say the asymptotic bounds hold.
But Christian, won't you need to have a notion of logarithmic growth or something like that?
Yeah, sure, but we have the log function for that, right? And I mean, you can either have a set that is called logarithmic growth, or you can just use the logarithm function. That's essentially my question. So do we need all these explicit names?
We'll get to try with the function first and then see if you actually need anything else.
I mean, I need some estimations, something like if S is at least log n, then n times, I don't know, some estimation. And I'm wondering if this framework helps there. I can check tomorrow. Then would it be then it would be really useful.
But my suggestion then is to have a look. This PR is huge, so a good way forward, if you told us that there are some devs and part of this PR that would be useful, maybe we can isolate that. We can ask Alex, could you make a smaller PR with this stuff? And then we put it in together.
Yeah.
I have another piece of news. A very smart undergrad from India reached out to me, and he pointed out that within this framework that I have, one can easily encode. You can take a divide and conquer algorithm, and for a different model, you can also get the memoized complexity or dynamic programming algorithm of it. And he's working on this for simple dynamic programming algorithms in my framework. And yeah, so this is very interesting already.
Very
this
nice.
is something that was discussed before.
Yeah,
in
yeah,
CSLib.
Yes. There's a now we have this multi-tape. I'm thinking about the definition of time and space in TMs, right? Because now we have both. Let's see. Let me see. This PR is huge. So we have multi-tape and single tape. Are the definitions in agreement in these two things?
Above linear space, they should be equivalent. Yes, I mean that's one thing. One next thing to do is to prove how they map to each other. Exactly.
Okay, so Fabrizio, in this case, I don't think they should map to each other because in multi-tape Turing machines, you can make a meaningful difference between total space complexity and auxiliary space complexity, whereas in single-tape Turing machines, this is hard.
Yeah, but I'm not worried about that especially. I'm more concerned about are we modeling similar things in similar ways without surprises, or do we have weird differences?
No, there are differences, but that's because the textbook definitions have differences.
Okay, so that's what I would call unsurprising, right?
Yes.
Okay, so for example, here we have state, fin type, Q0, and the TR.
One thing, so single tape TM does not define space at all. So it defines the space used by a tape, but it does not define the space complexity of an execution. And it's in certain ways, I think the definition might be wrong, but we will see if we when we show equivalence, if we have to adjust it.
I would suggest instead of showing equivalence, we try to go ahead with complexity because I'm more confident about the definition of space complexity in multi-tape TMs than the single-tape situation. Like Marcus Blazer told me at least we had a discussion and he told me openly that that Baraka definition is wrong, but for single-tape it's a little bit tricky.
Okay, so they do disagree. We have to fix it eventually.
Yes.
And here the space used, so another key difference is that we don't require any finiteness in multi-tape TM. maybe it's like-
Yeah, I think it's one of those situations where you put finiteness when you need it in a theorem.
Yeah, but exactly. I mean, this looks right, and single tape TM looks like we should remove the finiteness assumption.
Right. Yeah.
Yeah. So I
Okay.
put finiteness at the runs in time and space, I think, because there it makes sense. Required.
Yeah. And I remember there's the definition of space used, which is it is the natural extension of space used in the single tape, right? Not really.
No, it's different. So what I don't like, I'm not sure if we need to talk about the details, but what I don't like about the single tape Turing machine is that if you have a tape and you move its contents to the left, right? So you delete from the right and append to the left, then according to that definition, it uses constant space. And I think that shouldn't be the case.
Wait, say that again, sorry.
So you have a tape with some contents and you take from the right end and move it to the left. You delete it from the right end and append it at the left end.
Okay.
So you move the content to the left, and according to that definition, it requires constant space.
That should
Or is
require
it-
constant space, no?
Because
I don't know. I disagree. For multi-tape Turing machine, it's not constant space, but
Excuse me. Sorry. Okay, but it is using one extra cell space at any point of time.
no, because so if you delete it at one end and append it at the other end, the
Mhm.
definition just counts the number of non-empty cells on the tape, and that stays the same up to the round at least.
So you get one. Okay, my reading of that definition is that you get one extra. Okay, anyway, I think that definition is fishy in a different way. So let's focus on the multi-tape
Yeah,
version
exactly.
and prove some results first.
Yeah.
Because it's better understood.
okay. How are we defining? So the space used by a multi-tape machine, or in general anyway, I don't think it makes a super huge difference. But if the space used starting from a given configuration after T steps, right? Okay.
So what is your question?
I'm trying to reread your definition of space used by tape. Because you start from a configuration, you have T steps, and you have I tapes, right?
Yes.
Well, you have K tapes and whatever. Yeah. And now you are. I see. And this should
So
work also for non-deterministic Turing machines, I guess.
So the problem is I have this tm.configs, which is just a sequence of configurations. That, of course, doesn't work for non-deterministic machines. So that has to be adjusted a little. And for non-deterministic machines, sometimes you only count the space used by the accepting configuration. So it's also, we have to figure out which definition we want to use there.
Oh, you can't count the definition of any random. You have to pick an accepting configuration and pick that. Otherwise, you can go in crazy loops of using extra space and then reach the final result.
Would it help? Well, I don't know if it would help, but I'm just saying what we could easily make a lot of transition systems for these Turing machines, right? Because, for example, I could make a transition system that at every step, it tells you how many resources it consumed.
Okay, so the issue is the following. If you only count how many cells have been used in that step, and then I just, as Chris says, I keep shifting the cells used, I only end up using one extra space. But then by doing this, I create a bunch of extra spaces where I can put two counter machines and simulate them with extra O of one space. That is a Turing complete machine. So I create some space. Then I use it to simulate any problem in RE in O of one space. That's just not going to work.
Right. So that actually doesn't work for anything. You're right. Because what you're interested in is the maximal amount of space used during a sequence, or what?
The maximum amount of range. Okay, so you assume that you start with all the cells set to heads at the beginning, and then you say, well, what is the largest cell to which this head wrote ever?
Okay.
You accept you count the possibility that this head skipped over blank cells and then wrote at something at the end.
So
right?
it's like the maximum, the what is called, the largest position of the head over all tapes.
Where it wrote a non-blank value at
Okay.
any point related to people.
At any
And
point,
that's
yeah.
So as for the non-deterministic case, I think there you just say there exists a certificate, and for this, the machine reaches an accepting state if the language is the string is in the language, and then for that you say for this run you count the number of the maximum of this cells used. Okay,
So
I'm
is
entering
what
it
you're-
change. So sorry,
Is
I have
what
to
you're
keep quiet.
interested in observing the position of the head at each step?
I mean, in the end, you can reuse the space used by. Sorry, we can maybe change the space used by tape a little, or extract the part that deals with the actual configuration, and then go along a computation path, in another deterministic computation path, and use the max of space used by tape.
Yeah.
That could work. I'm not sure if, LTS. I mean, you could compute the space in the LTS state, but I'm not sure if this is more useful than just writing a simple recursive function.
I mean, as long as you are deterministic, the LTS is also a function. We have FLTS, so it's we're going to get exactly the same definition, I think.
Yeah, so I'm not sure if the abstraction for LTS is we gain anything from that.
That I don't know. I don't know. I'm just.
I think we will just have to try it out, and we can also
I'm
try
not.
both versions.
Yeah. I think you should. I think you should go ahead, and then one day, I'll try to slap LTS on top of the FLTS, not LTS. FLTS on top of this, just like I did for non-deterministic Turing machines.
Yeah.
And see if everything still holds, basically.
Yeah.
Because it should just be an implementation detail for a lot of the stuff that you're looking at.
Yeah, exactly.
I mean, it's not going to change your API. It's not going to change. It's going to change the internal API, but it's not going to change these definitions, I think.
Yeah.
Because
By the
you're
way,
still going to get a relation for the reachable configurations and so on and so forth.
Some master student reached out to me, and he asked how he can contribute, and I told him he can define non-deterministic Turing machines. So that's why I would hold off with that for now. For a little.
And I mean, what one gains from LTS is that, well, also in the future, is that there are ways to switch between the relational view and the co-algebraic view. So, for example, that you go from the non-deterministic transition relation to a function that gives you the set of reachable states with a single label, etc. All this stuff we should automate, and it should be general and shared. But these are, again, internal details that one would see in the proofs, right?
So I hope tomorrow I will open a pull request that has things like estimate the size of the configuration space and argue about if there's a loop, then it doesn't terminate and something like that. And it would be really happy for you to take a look at it and see if we can use that with LTS, or we can simplify the proofs with LTS.
Absolutely. Yeah, it would be nice to have a bit more because we with this, I mean, we still haven't done much in a sense, right, in terms of big proofs.
Can we target L subset of T for this? I think that's the best proof to put this to a test and still basic enough.
I couldn't hear you very well, Shreyas. Could you repeat?
L subset of T. log space subset of P polynomial line.
I will open a pull request for that tomorrow. So I have it. I just need to clean up the proofs a little.
Okay. All right. Cool. Anything else anybody would like to discuss? Excellent. Then I think we can adjourn to next time. All right. Thank you very much for joining us, everyone. Cheers.
All right.
Bye.
See you.